And I'm your TA. Today we will discuss the BK tutorial. Okay, so question number one is on your screen, and please try this. And question number one is the statement. You have to tell it is true or false. Question is that transmit diversity schemes allow array gain or not. Okay, again I'm repeating this question. Question one is transmit diversity schemes allow array gains or not. Please try this. Okay, if anyone got the answer, can comment or speak. Okay, so answer is the first question is the P part. Okay, basically in the when we are talking about a transmit diversity, there we can't achieve the array gain. Basically, if we describe what is the array gain basically gives an increase in the average SNR, while diversity gains means the probability density function of the instantaneous SNR more concentrated around its average value. We see in if you consider the case scenario of a transmitted diversity, there is a tough comparatively to the received diversity. Okay, question number two is on our screen. Try this. It's also related to the previous question. Question number two is that received diversity schemes allow array gain or not. In first question, we discussed about the transmit diversity. Yeah, here we are talking about received diversity. Receiver diversity means you have one antenna on transmitter side and two antenna on the receiver side. Just think about this and comment answer. Okay, please answer. Question number two is the received diversity schemes allow array gain or not. Again, I am repeating this question. Question number two is that received diversity schemes allow array gain or not. And received diversity means if you in this scenario we have one transmitter and one transmit antenna and two receive antenna. In this, if anybody know, can comment the answer or speak. Okay, answer is A part. It is possible to achieve array gain from the or the received diversity scenario. It will be A. Question number three is on our screen, and question number three is that what is the net degree of freedom for LMTE schemes for two transmit antennas? Here you have to calculate what is the net degree of freedom for LMTE schemes for two transmit antenna. already sir discussed LMTE schemes in the lectures. Again, I am repeating this question. Question is, what is the net degree of freedom for LMTE schemes for two transmit antenna? In transmitter side, we have two antennas. If anybody got the answer, please comment or speak. Okay. The answer of the question number three is the V. The explanation of this question is this: as we equivalently transmit two symbol over two channel uses, the net degree of freedom is one symbols per channel use. So answer of the question number three is the B part. It will be one. Question number four is a numerical question, and question is: a receiver has two antenna and perform maximal ratio combining to improve the BER. Both the receiver are uncorrelated and follow relief distribution. One of the antenna has an average SNR of 4 dB, another has an 8 dB average SNR. The average SNR after MRC is approximately. So we have to calculate the average SNR after MRC. Please try. From the first antenna, we are getting the average SNR is 4 dB, and from second we are getting 8 dB. Here we are using the maximal ratio combining techniques. So please try this question on your notebook. Again, I am repeating. Question is a receiver has two antenna and perform maximal ratio combining to improve the BER. Both the receiver are uncorrelated and follow relay distributions. One of the antenna has an average SNR of 4 dB, another has an 8 dB average SNR. The average SNR after MRC is approximately. Okay. Now we will see the explanation of this question. Okay. Actually, in MRC screens we add the average SNR of the all two values. Okay, basically gamma 1 is given that 4 dB and gamma 2 is the 8 dB. Okay, so we have to calculate average SNR after applying MRC. So firstly we calculate a gamma 1 gamma 2 in a linear scale. It is in a dB, so you can calculate by using the dB converter. 4 dB in linear scale and 8 dB in linear scale, so it will become 10 to 10 to power 0.4 and 10 to power 0.8. So just use your calculator, you will get 8.821, and our answer is given in a dB, so you can convert that. It will become 9.455. The answer will be C part. Now question number 5 is a statement question. Okay. Question is, which of the following statements is not correct? And this all statement is given about the array gain. First is the array gain is absent in a non-feeding environment. Array gain causes a shift in a VR curve. Diversity gain improved the statics of the SNR in a way that reduced the VER, or all the above. Just use the basic concept of the all the above. Please try again. Hello. No, I'm talking about which statement is not correct. Yeah. Okay. Again. Yeah, yeah, you're going close. By intuition, you can say that the C part is the right. C statement is correct. B is also correct. Yeah. Uh, A is the right option for this question. A again is absent in a non-feeding environment. Okay. So A part is the right answer. Okay. Question number 6 is now on your screen. And the question is, consider a channel with SNR is 20 dB. What is the capacity of the channel per unit bandwidth? Please try. Just simply use the formula of the capacity to calculate the capacity. I'm giving you a hint. You can use the formula of C is equal to V log 2 1 plus SNR. Just put the value of SNR. From there you can get the capacity. Ankit, are you trying? Yeah, yeah. What is the capacity of the channel per unit bandwidth? Just use the formula C is equal to V log 2 1 plus SNR. Yeah, yeah. Firstly, converting linear. Yeah. Okay, this is the explanation. I think it's we are getting 6.6 something. Okay, yeah. I just said that base is 2. Okay, I think it's clear. Just because it's talking about the channel per unit bandwidth, so it's V is equal to 1, so it will become 6.6. So can we move to next question? Okay. Question number 7 is on your screen. Try this. For a Nyquist pulse shaped signal with unique average signal power, the capacity of channel depends on. It's a reasoning based question. Basically, you have to tell the capacity of the channel depends on which parameter. And this is the condition. Again, I am repeating, for a Nyquist pulse shaped signal with a unit average signal power, the capacity of the channel depends on. Here, units average signal power. Hmm? Again, rethink about the question. No, no, no. Question is, here you are using the Nyquist pulse shape, and given is that average signal power is a 1. Then you have to told the capacity of the channel depends on. Signal power is 1. Here you are giving your answer by intuitively. Just write the formula and the capacity and try to play with the symbol. No, no. Okay, okay. The explanation of this question is given that. Okay. Basically, this is the formula, right? C is equal to V into log to 1 plus SNR. And here you can write SNR is equal to signal power upon noise power. Okay. And when you go, you can write your noise power is equal to N naught into V. Here PS is the one as the given in the question. Variable is only the B because N naught is mostly constant. So here you have a 4 option. Okay, modulation scheme, receiver sensitivity, symbol rate, and you have to calculate the symbol rate using the V. So it will be C part. Okay. Okay. C will be the right answer. Okay. Next. Okay. Hmm. Basic. Yeah, these all parameter actually depend, but for this, it will be C part. Indirectly, all the parameter modulation scheme affect receiver sensitivity. Okay. Okay. Next four five question are correlated. Okay. Data is same. The question number 8 is the first law. I will discuss about it data. Consider a fading channel with the instantaneous SNR given by gamma is equal to alpha square, where gamma is the SNR is the 20 dB and alpha is the instantaneous fading coefficient that vary with the time and with the 20 kilohertz. The probability density function alpha is follows. The first question is the what is the average SNR of the channel? Using this data, you have to calculate. Firstly, you have to calculate what is the average SNR of the channel. Please try this. Alpha is the instantaneous fading coefficient, and the probability of alpha is given in this table. These states are varying with time. You have to calculate average SNR. Again, I am repeating this question. Instantaneous SNR is given. We have alpha. We have the instantaneous fading coefficient that vary with the time, and the table representing the data. You have to calculate what is the average SNR of the channel. Anyone got the answer? Okay. So we have to calculate the average SNR. Okay. So this is the explanation. What do you say? I think, yeah, yeah. When you will calculate that, it will. I think you will get 0.85. Just so firstly we will calculate this term using this. Firstly calculate this term by using. Yo, yeah. Maybe, but I think answer is the C part. It, firstly we will calculate this term. I think it should come at 0.85. Please let me know. It's coming 0.85 or it's not. It's coming at 0.85 or not. This summation. Okay. What you are get? What you are getting? Okay. To calculate the average SNR, firstly we will calculate this or using okay, or we using this stats. We just multiply your 20 dB. That is given 20 dB. So from there you will get 19.3. You can try your with Calci this question. Okay. Yeah. Okay. Okay. Try this, and if you have doubt, you can post your question. Use doubt on discussion forum. Okay. Okay. We moving for the next question. Next question also correlated with this data. Now we have to calculate, can you find an upper bound on the channel capacity using Johnson's equality? Data is the same. Here we have to calculate, find an upper bound on a channel capacity using Johnson's equality. Again, here we have to calculate channel capacity using Johnson's equality. Okay. Already we calculated our SNR. Okay. So just multiply the bandwidth is given a 20 kilo. Uh, sorry, bandwidth is given a 20 kilohertz. Okay. For the question 9, question bandwidth is given a 20 kilohertz. Okay. We have to calculate the upper bound of the channel capacity. So we just use the formula of the capacity. C is equal to V into log 2 1 plus average SNR. I think we calculated the average SNR on the last question. Just multiply with the V is the 20 kilohertz. From there we can get our capacity. It will come 128.53 kbps. For a cross check, you can try this on a notebook. Okay. Now question number 9 is given. Here we have to calculate what is the ergodic capacity of the channel. Last question we calculate the upper bound of the channel capacity. Here we have to calculate what is the ergodic capacity. Please try this. Anybody got the answer? Okay. So here we have to calculate ergodic capacity. So for for this we will use this data. Okay. So we just multiply with the this terms. Uh, we will calculate we will calculate SNR for every term, every I, and with its probability, and it's there is a 4 values. Just calculate and sum the all values. From this formula we can calculate this. For every value of alpha, calculate this, and again after that sum all 4 values. V is the constant for R. It is 20 kilohertz. Just it will come 5.84. Just multiply with the 20 kilohertz. So it will become 116.8 kbps. Okay. Now question number 9 is question number 11 is what should be as. Yeah. Sorry. Okay. Sorry. This Okay, what is the okay overall what you're getting from the what is the value you are getting for this function? Sure. I think we have to recalculate it. I'm sure we have to just get just put the value of the average SNR that we got on the last question. Okay. Okay, I will also check this. I think it will come 128, but I will try. I will also check it. Okay. Question number 10 is clear. Here we have to calculate the ergodic capacity. Okay. Now question number 11 is what should be the SNR of a flat feeding channel that has the same capacity as the ergodic capacity of the feeding channel discussed above. Again, I'm repeating what should be the SNR of a flat feeding channel that has the same capacity as the ergodic capacity of the feeding channel discussed above. This question we have to calculate SNR, and given that capacity is same as the ergodic capacity of the. Okay, the explanation of this question is there. So just assume the let SNR of the flat feeding channel is the gamma, not 10. Okay, it is given that it is same as the ergodic capacity. Okay, so I think we have calculated the ergodic capacity in the last question is 116.8 kbps. So for this scenario, ergodic capacity is same as the capacity. So just put this value is equal to 116.8 into 10 to power 3, and from there you can calculate the gamma and calculate the SNR, and it will become 56.28, and the dB it will become 17.50. If anyone have doubt, please ask. Simply just put the value same as the formula of capacity. Condition is given, ergodic capacity is same as the. Okay. Now question number 12 is what is the ergodic capacity of the channel discussed above if there is a 99% chance of the outage at any time? Again, what is the ergodic capacity of the channel discussed above if there is 9% chance of the outage at any time? Yeah, yeah, you're going right. What you getting the answer? Okay, we have to calculate what is the ergodic capacity if there is a 9% chance of the outage at any time. Okay, so uh, for this ergodic capacity with outage, we just multiply with the 1 minus p outage. It's given as the 9%. Okay, so it will be 0.9 and multiply with the capacity with the outage. Capacity with the outage is the 116, and but multiply with the this probability, it will become 106.29. You are doing the same thing? Hello, sir. Okay, thank you. I think it's clear now. Okay. Next question is a statement question. Okay, question is that which of the following is our valid mode to obtain CSIT? We have four options. How we obtain the channel state information at a transmitter end? I think it's reasoning based question. Please answer. Yes, right. Anybody? Okay. Uh, A and B both is the right option. So C will be right part of this question. This question. Okay. Uh, okay. Okay. You're saying that we have no CSIR at receiver end. So what we have to obtain? Okay. Yeah, thing I'm okay. Okay. This is an example of the TDD system. Um, time. Okay. Uh, for a TDD system, CSI can be locally estimated by a transmitter and for an FDD system. Sorry, for a TDD system, CSI can be locally estimated at a transmitter, and for the FDD system, we can feedback the CSIR. Because TDD system, uh, we can doing the same. We are using the same frequency for FDD system. Yeah, for the uplink and downlink both for the both we are using the different frequency band. So from there we can calculate by using the feedback. C part will be right. Next question is, one method to overcome fading in a CSI scenario is to use long code words that cover all possible fading states, which is a problem in using such a system. Again, I'm repeating, one method to overcome fading in a CSIR scenario is to use the long code words that cover all possible fading states, which is the this is or a problem in using such a system. Yes, right. Okay, pro. Yeah, both options affect our performance. So our system performance. So C will be right. Okay. And the last question of today's session. Question is: say you have a three independent channel with SNRs gamma 1, gamma 2, gamma 3. What should be the order of the P power allocation to maximize the capacity? Again, we have three independent channel with SNRs gamma 1, gamma 2, gamma 3. What should be the order of power allocation to maximize the capacity? Think No, no. Okay. I think it's will A. There we are talking about what should be the power order of power allocation to maximize the capacity. Yeah. 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 It's talking about the we have to maximize the capacity. Okay. I think it's over for my side. Okay. Sorry, sir. I am using the same thing. Okay. We have to put 10 base. We always have to put the base to 10 or whatever we are. Okay, sir. Thank you for joining. Okay. Thank you, sir. Thank you, sir.